Hello, welcome back to this channel. My name is Dr. Arzu Jabra, and I have a PhD in organic chemistry. And I'm also a mindset academic coach for college students. So I help college students who are stressed out go from feeling overwhelmed, feeling stressed, to actually feeling a lot more excited, a lot more focused, and a lot more in control of their life, whether you are preparing for MCAT or you're just getting some college blues. So that's about me. And today we're studying or learning the isomers. So I will be solving the second chapter from Kaplan for the problems in Kaplan that are the organic chemistry problems, helping students get ready for MCAT. All right, so let's get started. So the first problem is, which of the following do not show optical activity, right? So let's just highlight the word do not show optical activity, right? So the first option is R2-butanol, right? The second option is S2-butanol. The third option is a solution containing 1 molar R-butanol and 2 molar S2-butanol. The last option is a solution containing 2 molar R2-butanol and 2 molar S2-butanol. Okay, so we know if a compound is has a chiral center, right, then it does show optical activity. So for example, the first option is R, so it does have an optical activity because it has a chiral center. Okay, second option, S2-butanol, and again, it does have a chiral center, which is an S. Okay, the third option, a solution containing 1 molar R and then 2 molar S. So effectively, what we do know is that if you have 1 molar and 2 molar, right, the solutions, then, and one of them is R, and if the other one is actually just an S, then what we do know, right, is that 1 molar R will cancel the optical activity of 1 molar S, because if R will rotate the plane of polarized light towards the right, for example, it can also do the left, hypothetically speaking, right? So then the 1 molar S will actually rotate that plane of polarized light more towards the left, right, or the opposite direction. And then when they do that, they cancel out the optical activity. All right, so but if you have 1 molar and then the other one is 2 molar, so there's still that excess of 1 molar present, right, that will effectively rotate the plane of polarized light in one direction, and that is why then C will actually show optical activity. But then if you look at option D, right, a solution containing 2 molar and 2 molar, so yes, they're equal proportions or equal concentrations, and therefore they will actually cancel each other's rotation out. So D is actually the correct answer for this option. Okay, next problem. How many stereoisomers exist for the following aldehyde? Okay, so if this is an aldehyde, how many stereoisomers exist for this compound? Okay, so we're going to think about it. Let's really fast think about the formula for a stereoisomer, which is stereoisomers. The formula is 2 raised to the power of n where n equals the number of chiral centers. Right? So now effectively we have to find the number of chiral centers present in this Fisher projection. And again, reviewing really fast. Okay. Hold on, I think I need to take this one call. I'm gonna pause this here for a hot second. So then let's review really fast what a chiral center is. A carbon which actually has 4 different carbon centers is actually called a chiral center, right? So if you think about it, this carbon over here actually, this carbon over here actually is a chiral center, right? 1, 2, 3, and 4. Okay, and then the second one is actually, this is a chiral center because it has 4 different substituents, right? 1, 2, 3, and 4. Okay, and then the third one actually is over here, which also then has 4 different substituents. So again, 1, 2, 3, 4. Okay, so 1, 2, 3. So we do see, okay, how about the last one? Is that actually a chiral center? That's actually not a chiral center, right? Because it has the same hydrogens. So what we do really see here is that we've got 1, 2, 3 chiral centers. So then the number of stereoisomers is 2 raised to the power of 3, right? Which actually then is 8, right? 2 raised to the power of 3, it's actually 8. So this compound actually just has like 8 chiral centers, or sorry, 8 stereoisomers. Okay, which of the following compound is optically inactive, right? So same as the first question, where we said that, okay, if we have a compound and that is that has a chiral center, right? That compound is actually optically active. So a compound which does not have chiral centers are optically inactive, but then also compounds that are meso compounds, remember, are also optically inactive compounds. And also, by the way, I will attach the PDF of this problem set as like a link down below. And if you're interested, of course, feel free to download that and then double check your answers from this video, or even pause this video and work through it. And if you have, of course, any problems or any questions while solving it, then you can double check with my explanation. So which of the following compound is optically inactive, right? So then effectively, either we're looking for a meso compound or we are looking for something that does not have chiral center. So the first compound does have 2 chiral centers over here. So it is actually a inactive, or sorry, it would actually make for a active compound because it is chiral. The second one is actually also an active compound. The only difference is that it is reversed, right? It's like inverted first compound. So if you invert the first compound, move it like 180 degrees, then you'll actually get compound B. So compound B is actually also an active compound. If you look at compound C, then compound C is actually the meso compound, because meso compounds are compounds that actually have a plane of symmetry. And we do see that there is a plane of symmetry over here. And then whenever we have a plane of symmetry, the compound becomes optically inactive, and we call it a meso compound. All right, so we do see option C is the correct answer. Let's look at option D really fast. Again, option D also has a chiral center, which is over here, only has 1 chiral center, right? The bottom one actually is not a chiral center. So then that actually is a, that one is a active, optically active compound. All right, so then next problem. Identify the chiral centers in this compound. And again, really fast, what the definition of a chiral center is the number of carbons which contain 4 different groups on that center would be the chiral centers. Okay, now if you look at the carbons, then you've got this carbon center, first group, second group, third group, and the fourth group, right? So we do see this carbon as the chiral center. Okay, and then there's this carbon over here, which is one group, and we do look at the full attachment, right, when making the comparison, which is different from this group, right? Second attachment. The third attachment is over here. The fourth attachment is a hydrogen, which is an implied hydrogen over here. Okay, so then this is this. And so this is our second chiral center. Now, if you look at this carbon over here, this actually is a third chiral center, right? Again, one different group, second different group, third group, and then the fourth group. Okay, all right. And then how about this one? Is this a chiral center? So let's look at it again. First different attachment, second different attachment, third attachment, and the fourth attachment is like that carbon group. So that's also a chiral center, 1, 2, 3. And about this one over here, okay, and then I've got first different attachment, second different attachment, third attachment, fourth attachment. So all of these are different attachments, different groups, also a chiral center, right? Over here, we've got first attachment, second attachment, third attachment, and then we've got the hydrogen, so which is actually a fourth attachment. Also a chiral center. This carbon over here, right? So we've got one attachment, different, second, third, and fourth, also a chiral center. Okay. And then of course, at any time you see a CH2 group, right? So this is a CH2, just discount that right away as a chiral center because the moment you see two groups similar, so we've got it, hydrogens, and that's not actually a chiral center. CH2, not a chiral center, CH2, not a chiral center. And then we've got a carbon, right, with hydroxide, hydrogen, this group, and with this attachment, which is completely different from this attachment, right? Because we're not just looking at the first point of attachments, which are CH2s. You might think, oh, they're exactly the same, but then there are more connectivities to it, and the whole connectivity or the whole group that's attached is very different from the entire group that's attached over here. So that would make for a different attachment. So then this carbon also has a different attachment. So then you've got 1, 2, 3, 4, 5, 6, 7, 8. 8 different chiral centers. And again, this is a CH2, not a chiral center. And this carbon actually has CH3s, right? CH3s are definitely, has 2 of the same group, which are CH3 and CH3. So again, cannot be a chiral centers. So let's see if there's an option for 8, and there is. So the third option is actually the correct answer for this problem. Okay. Which of the following isomer is, which isomer of the following compound is the most stable? Then when we look at the chair conformers, we know that if you have groups that are present on the equatorial position, then they are more stable, right? Groups that are present in the equatorial position, because at the equatorial position, we don't see any 1,3 diaxial interactions. When you don't have the axial interactions, the compound doesn't experience repulsion. And if there's no repulsion, then it's, or the electron-electron repulsion, then it is a stable compound. So now if you look at A, B, C, and D, right? D is not an answer. Okay, it might be. Let's check. For C, it's a boat conformation. A boat conformation is definitely not a stable conformation. And now if we look at amongst A and B, right? A has a group which is axial, right? And this is equatorial. So 2 groups that are equatorial are more stable than 2 groups that are axial. And so then option B is actually the correct answer for compound, or for problem 5. All right. Which of the following reaction results in, the following reaction results in. So there is a reaction over here. And what do we see in the reaction is that the reaction is with acyl chloride and hydroxide. So the hydroxide, right, actually reacts with acyl chloride. So this looks more like an addition reaction on the carbonyl. And of course, this is more like more actually from an orgo point of view, it's actually Orgo 2 reaction, right? The addition reaction of carbonyl compounds. So if we just look at the reaction for now and not really dig into the type of reaction, then what we really see here is that a retention of relative configuration and changing. So they're asking if the relative configuration is changing and what's happening to the absolute configuration, right? So let's think about how the cis trans or the diastereomer, not really diastereomerism, but like think about how my pencil died. Hold on, give me 1 second. Right, so we're talking about the retention, right, or the relative configuration. So relative configuration is more like cis and trans. Would the cis and trans actually change? Meaning, would the two groups, which are with respect to each other, if they are relatively cis to each other, would that affect the product right now? Meaning, if the two groups that were relatively, let's say, if we really think about it, let's use the two groups as, at this point, CH3 and OH, right? They're relatively trans to each other, right? And then if you think about it, is that changing, right? The two groups which are of higher priority, so let's say the one with oxygen and then the CH3, they're still trans to each other, so that's not really changing. And then here's the other thing, relative or absolute configuration really means if the R or S is actually changing, right? But here's the thing, right? Oxygen was still the highest priority and oxygen was still the highest priority, and we do see the retention and configuration. And because we do see the retention and configuration, what that really means is that the RS would actually stay the same. And same thing with relative configuration too, right? Because we have a relative, the group which had the highest priority remains at the same position. Nothing is really changing. The configuration is actually remaining the same. Like the wedge bond still remains on the wedge bond, right? So then we can actually say that that they both remain the same. The retention and absolute configuration, or the retention of the absolute and the relative configuration is happening. All right, long-winded answer to an easy problem. Okay, the following is a pair of what structures? So if we really think about it, right, we do really see these two structures are mirror images of each other, right? When you see compounds that are mirror images of each other, we can say that they're actually enantiomers. Okay, and diastereomers are not mirror images of each other. Means the compounds have plane of symmetry. Structural isomers are compounds that are not chiral, and they have same chemical formula but different structures, right? So that was pretty straightforward. Let's get to the next problem. Which of the following is a pair of what structures? Okay, is that the repeat problem? Yes, okay. All right, okay, so like this chapter only actually had 7 problems to go over. And so with that, we come to the end of the second chapter. And very soon I will be making solutions or explanation for the third chapter from Kaplan, right? And I do plan on adding a lot more resources for MCAT help for chemistry and Orgo, and really help you guys prepare well for this exam. And if you have any questions or if you want my help, feel free to reach out on the links which will be mentioned down below. And until then, keep learning and keep growing. I will see you guys next time. Bye now.